Dear viewers, welcome back to part 2 of our exciting journey through the 7 questions. In the first part, we explored flow diagram, check sheet and cause and effect diagram, which helped us understand processes and identify potential causes of problems. Now get ready to dive into the next set of powerful tools. In this second part, we'll explore the power of histogram, Pareto chart, scatter plot and control chart. These are essential tools for visualizing data and gaining deeper insights into the quality challenges. Before we begin, I want to express my heartfelt gratitude to all of you who watched part 1. Your support means a lot to me. If you haven't, I kindly request you to consider subscribing by clicking that subscribe button and becoming a part of our quality Munch community. Your subscriptions truly motivate me to create more valuable content and share knowledge with you. So let's explore these next 4 tools together. A histogram is a visual tool that displays the frequency or occurrence of values in a data set, showing how they are distributed. Let's explore the 3 key points about histograms. It helps identify patterns, outliers, and data characteristics like central tendency and spread. Analyzing a histogram helps identify deviations and potential issues in the data. Histograms help assess process capability by comparing measured values to specified limits, and that's the essence of histogram, a powerful visual tool for understanding data distribution and assessing process performance. Here in this slide, we have a histogram showing the weight distribution of tires in different weight brackets. Let's explore the key measures. Mean or average. The mean weight of the tires is 159.7 kg. Mode. The most common weight is observed 159 kg. Median. The middle value of the data is 160 kg. The histogram shape resembles a normal distribution, indicating a good fit for this data set. By superimposing specifications with the tolerance range on this histogram, we can evaluate how many values fall within the acceptance zone and how many values fall within the rejection zone. For this specific data, only 1% of the values above the upper tolerance are getting rejected. In the right side, you can see the different shapes of histogram, which shows the different types of behaviors of the data. In order to learn histogram in details, you must watch my videos which I have created specially on histograms, along with step-by-step tutorials in MS Excel and Minitab, explaining how to plot histogram easily. You can find these videos on this channel, Quality Munch. Welcome to this slide, Pareto Diagram. A Pareto diagram is a special type of column graph used to prioritize problems or opportunities. It helps teams focus on the areas with the greatest impact. Named after Wilfredo Pareto, this chart follows the 80-20 rule, helping us identify significant factors that contribute to a problem. Pareto charts are widely used in quality management and process improvement to pinpoint key areas for improvement and make informed decisions. And that's the power of Pareto diagram, a tool that simplifies decision making and guides us towards the most critical areas of improvement. Here in this slide, we have a Pareto chart representing the area-wise power consumption of manufacturing plant. You can see the Pareto chart combines information on the x-axis for different areas. Y-axis is for power consumption and secondary y-axis is for cumulative percentage of power. Let's analyze the insights from this Pareto chart. 3 areas, namely machine, hot water and air system, are consuming 78.9% of the total power consumption. These areas are the vital few that have the greatest impact on power consumption. The remaining areas like stock preparations, lighting, canteen, air washer, HR, store, hydraulic and makeup water contribute only 21% of the total power consumption. These areas are the trivial many with relatively lower impact on power consumption. By this visual representation, the Pareto chart allows us to clearly identify where we need to concentrate our efforts for the most significant impact. Welcome to this slide, scatter diagram. A scatter diagram is a powerful graph that shows the relationship between two variables. It helps us understand how one variable depends on the other. In a scatter diagram, the dependent variable is represented on the y-axis, while independent variable is shown on the x-axis. By observing the points on the scatter diagram, we can easily grasp the relationship between two variables. Clustered points suggest correlation, meaning that the variables have a connection. On the other hand, scattered points indicate no correlation, suggesting that the variables may not have a clear relationship. However, even if the scatter diagram shows a relationship, we must not assume that one variable caused the other. Both variables could be influenced by a third unseen variable. And that's the essence of scatter diagram. A valuable tool to help us visualize and comprehend the relationships between variables. Here we have a scatter plot showing the relationship between training hours and defect. Did you know that as we increase the number of training hours, something amazing happens? Yes, employee skill improve and the number of defects significantly reduces. Observe this interesting data. For just 1 hour of training, we see 33 defects. But wait, as we extend the training to 3 hours, the defect dropped to around 25. And guess what? For 5 hours of training, there are only about 2 defects left. By the way, when we fit a straight line through these points, we find a negative linear correlation between training hours and defect rate. Now let's explore different ways of how two variables can be related. If the points approach from left to right going upward, it indicates a positive linear correlation. But if they come from the left heading up and then going down to right, it shows a negative linear correlation. Oh, but not all relationships are straightforward. Some points form artistic curves indicating a non-linear relationship, while others scattered between x and y axis show no clear relationship at all. A control chart is a powerful tool used for statistical process control. It helps us monitor and analyze process variations over time, aiming to identify and solve problems or process improvement. One of the fantastic features of control charts is their ability to distinguish between two types of variations, special cause and common cause. By comparing data points to control limits, control charts allow us to determine if a process is stable or experiencing unusual variation. This valuable information assists in problem identification and enables timely intervention, leading to effective process improvement. Isn't it fascinating how control charts provide a visual representation of process performance and help us achieve consistency and quality? Here we have a control chart showcasing an example with upper control limit and lower control limit. It's essential to understand that these control limits are not specification limits. Instead, they are derived from the natural behavior of data, specifically 3 standard deviations away from the data's mean. Let's walk through the process. We start by collecting samples in rational subgroups, like 5 samples in one subgroup. These samples are the snapshot of the process at that specific time. Now, if you notice a point like the one in red below the lower control limit, it means something special might be happening. At this point, it's crucial to stop the machine and investigate the reason behind the out of control value. Below the control chart, you will find various patterns representing the behavior of the process, such as shift, drift, oscillation, mixture of data, excessive out of control, trend and cyclical behavior. Control charts are incredible tools that help us understand process performance and identify unusual variations so we can take prompt actions for process improvement. Here we will explore the different types of control charts depending on the type of data we have. If we have continuous or variable data, we follow this approach. We use individual moving range chart when we have only one sample as a subgroup. It helps us monitor individual data points and their ranges. We use X bar and R chart if we can collect samples in subgroup. Let's say 2 to 8 samples in one subgroup. It helps us track the subgroup averages and the ranges. We use X bar and S chart when we have more than 8 samples in one subgroup. It allows us to monitor subgroup averages and standard deviations. Now, when we have attribute data, it's a different approach. There is a P chart if we are collecting data on defective items. Example, the number of defective units in a sample. It helps us monitor the proportion of defective items. We use U chart if we are tracking data on defects. Example, the number of defects per unit. It allows us to monitor the number of defects in a sample. For better understanding, let's differentiate between defects and defectives. Defects refer to the number of issues or problems identified in a single unit, while defectives represent the number of units that contain at least one defect.